Hello everyone, welcome back to my channel. In this video, we will be discussing about the third part of our explainable AI series, that is counterfactuals. So here's the situation. You're applying for a loan, you fill out all your details, loan amount, income and credit score. And the model says you have a 40% chance of approval. So basically you're denied. Now you're thinking why? So that's where explanations come in. The model explains that income is a big factor in the denial. So it's too low for the approval threshold. That is 50%. Okay, but here's the thing. Knowing why your application was denied is helpful, but it doesn't solve your problem, right? You're still denied. So this is where counterfactuals come into picture. It answers the question, what can I do to change the outcome? So, for example, the model might say if you increase your income to $60,000, your approval probability will jump to 70%. So, counterfactuals take us from explanations to recommendations. So, here's a healthcare example. The system flags a patient as at risk for diabetes with a BMI of 28 and fasting glucose of 100. But the counterfactual suggests that if the patient reduces their BMI to 25 and glucose to 95, then you're no longer at risk for diabetes. Now, here's a job application scenario. A candidate isn't shortlisted with 2 years of experience and 2 certifications. So, the counterfactual suggests that gaining one more certification might help the applicant to get shortlisted for that particular job. Let's take an example to understand how we evaluate counterfactuals. Here we have got some loan data with details like loan amount, income, credit score, and approval percentages. Now, when we are evaluating counterfactuals, there are a few common metrics that we can use to see how good a counterfactual is. The first one is coverage. Then we have prediction gain. Next, there's distance. And finally, plausibility. Now, there are more metrics that you can use, but in this video, we'll be talking about these 4 metrics specifically. So let's have a look at each one of them in a bit of detail. Let's start with the first metric, coverage. Coverage tells us how many instances actually have valid counterfactuals generated for them. So over here, you can see that we have 3 instances where the loan was denied, and we want to find the counterfactual for each of them so that we can see what changes needs to be made for a loan approval. So over here you can see that for this instance the counterfactual was successfully generated. For this one also it was generated. However, for this one it was not generated. And that's what coverage tells us, which is the number of instances with counterfactuals divided by the total counterfactuals that have to be generated. Now in this case, 2 counterfactuals were successfully generated. So we have 2 out of 3 counterfactuals that had to be generated. So that gives us a coverage of 66.7%. Next up, we have prediction gain. This is also pretty straightforward. This metric measures how much better the approval rate gets after applying counterfactuals. So over here we can see that the first instance we jumped up from 40 to 75%. So that gives us 75 minus 40. For the second instance, we jumped from 55 to 30. That gives us 55 minus 30. And since 2 counterfactuals were generated, we divide that by 2. So we get a prediction gain of 30%. Okay, so now let's talk about distance. This metric looks at how much change is needed to move from the original instance to the counterfactual. And here's the breakdown. So first, for each instance, we calculate the distance for all the features. Then we sum up these distances across all the instances to get the total. Finally, we divide that by the number of instances to get the average distance. So smaller distances mean less drastic changes are required, making the counterfactuals kind of more practical. So in the first step, we calculate the differences between each of the feature among all the instances. So d1 is the distance between all the features between this and this. d2 is this difference between all the features from this between this. Then we take the total distance, which is this, and then we divide that by 2. So in a more real world scenario, it's very important to scale the features, because without scaling, features like income or loan amount could really dominate the distance calculation. So once features are scaled, then we can sum up these distances across all the instances to get the total, and normally do the average calculation by taking the total, dividing it by the number of instances. So now let's talk about plausibility and how we can make sure that a counterfactual explanation is realistic or not. And let's try to understand this visually so that it is a bit intuitive to understand. So first, take a look at all these blue points on the graph. They represent the original data points or actual observations from the data set. Now what we do is we add gray points to this data, which are counterfactuals. So all these gray points that you can see are the counterfactuals which are generated from the data. Now out of these, you can see some are closer to the entire data set and some are a bit further away from the data set. So the ones which are closer to the data set are considered as plausible counterfactuals, because they kind of resemble the original data points. However, the ones which are further away from the data are considered as implausible counterfactuals, because they don't fit the patterns of the data very well. And we'll discuss this through an autoencoder. We'll understand how it works and how it can be used to quantify the plausibility metric. Alright, firstly, let's talk about the autoencoder. And this is a type of neural network we use to check if counterfactuals are plausible or not by comparing them to the patterns in the original data. So let's see how the training of autoencoder works and the whole intuition behind reconstruction error. So on the left, we have the training data. So these are fed into the autoencoder. The encoder compresses them into a latent representation. For instance, $10,000, $45,000, and 720 might get compressed into something like 0.8 and negative 0.5. So the decoder then reconstructs these compressed values back into the original features. For example, 10,000 might get reconstructed as 9,900. 45,000 might become 45,500, and 720 might become 700. So the difference between the original and the reconstructed values gives us the reconstruction error. And the autoencoder adjusts itself during the training to minimize this error. So meaning it gets better at capturing the patterns of the data over time. Now let's see how autoencoder can help us evaluate counterfactuals and see whether a counterfactual is plausible or not. So here's a counterfactual: increase income to $65,000. The autoencoder takes this counterfactual and tries to reconstruct it. Now, if the reconstruction is close to the counterfactual, it means the changes align with the patterns the autoencoder learned during training. So the counterfactual is basically plausible. But if the reconstruction error is high, it means that the counterfactual doesn't fit these patterns inside the training data, which means it's implausible. Okay, so let's take a real world example to kind of understand how a counterfactual method works. It is called as NICE, Nearest Instance Counterfactual Explanation. And the link to that paper can be found in the description. So feel free to check that out. Okay, so let's take this step by step and see how it works. In the first step, we focus on this red dot that we have, and it represents the original instance. Now what we'll do is we'll start looking at instances that are approved and kind of on the other side of the decision boundary, right? So here's one applicant whose loan was approved, and here's another approved instance. Finally, we have the third approved instance. And one important thing to note is all these green instances, which are on the other side of the decision boundary, but are also kind of closer to this original instance, right? And they are something called as nearest unlike neighbors. So what we'll do is we'll take this nearest unlike neighbor and use that to find the counterfactual for this red dot that we have over here. So now let's look at step 2. Here's where NICE starts building potential counterfactuals by swapping features between the original instance and the nearest unlike neighbor. So let's walk through this process so that we have a better understanding. Uh, the original instance has a loan of 10,000, income of 65, and credit score of 720. And the neighbor has income of 68,000 and credit score at 700. So what happens next? NICE swaps one feature at a time to build this swaps table. So hybrid 1, we keep the income and credit score from the original, but take the neighbor's income of 10,000. In hybrid 2, we keep the loan amount and credit score same, but take the neighbor's income of 68,000. And similarly for hybrid 3, we keep loan and income the same and swap the credit score. Now we evaluate these hybrids. So each hybrid is evaluated to see how much it improves the prediction towards approved. So this is done using a reward function, which we'll discuss shortly. The hybrid with the highest reward is chosen as the new best instance for the next iteration. So say for instance, hybrid 3 has the highest reward in the first iteration, and NICE updates the original instance to this hybrid. So now loan amount becomes 10,000, income becomes 68,000, and credit score is 700 because it borrowed credit score from hybrid 3. So if this updated instance still predicts rejected, NICE will repeat this process again of swapping different features in subsequent iterations. And the stop condition is it continues until the instance flips its prediction to approved. And once this is achieved, NICE stops. So if you notice, it always guarantees 100% coverage, because in the worst case scenario, after going through all the iterations, original instance will become equal to the nearest unlike neighbor and just return that. Okay, so there are 3 versions of NICE. In this, we'll have a look at 2, which is NICE plausibility and NICE distance. So versions typically means the reward functions that NICE uses to assign to each of the hybrid that we discussed in the previous slide. And as you can see in both of the versions, NICE plausibility and NICE distance, what it tries to do is it tries to maximize the prediction gain and tries to minimize either the reconstruction error or the distance. Okay, so now we'll have a look at some of the limitations of NICE, and also it's a good example to see what kind of things we should be looking at when choosing a counterfactual method. So the first one is feature mutability. Now this is kind of important in the real world scenario, because if you can see from the example, if there is a feature called as gender and the counterfactual suggests that you need to change your gender from male to female in order to get your loan approved, so that is something that is completely wrong, and we need our algorithm to avoid that. So in order to do that, it is important to make some of the features immutable based on the data that you're using, basically. And the next one is feature ranges. And from the example, you can see that, say, suppose there is an e-commerce company that needs to give discounts to their customers in order to retain them. But it also has some kind of policy that they don't want to give discounts of more than 20%. Now, this is also important for the model to incorporate so that the model doesn't give unrealistic discounts to the customers, like 50%, 70%, like that, in order to retain them. So depending on the business logic, it is important to have these kinds of functionalities inside the algorithm that you're using. And that's it for today's video, guys. I hope this helped you understand them better. If you've got any questions, feel free to drop them in the comments. Thanks for watching and see you guys in the next one.